Welcome to Module 4 of the SRE Practitioners course, and we're going to talk about full stack observability. So the module has three major items in the syllabus. First of all, we'll talk about essentially why observability is important, because modern applications are pretty hard to observe unless you build in observability. And then we'll talk about how you do that, how you actually make observability work, and how you can implement it through monitoring and telemetry and other things. So the structure of the module is the same as all the others in this series. There's a video, actually there's a couple of videos about open telemetry. It's a standard for communicating information about observability and monitoring, and some of the ways that you can implement observability in real systems through Prometheus and Zipped and a couple of other ideas. There's a case story. We're going to allow you to do a couple of activities, basically, how you can implement full stack observability and how you can bake observability into your software, into software. So the first thing is thinking about modern applications. This is really underpinning the idea of why observability is important rather than just traditional monitoring. Traditional monitoring is still relevant and important, but the idea is that you need something more than just traditional monitoring. You're going to need to understand a lot of the intricacies of how systems work and how do you get data from those systems in order to be able to determine in real time when you have very dynamic systems, what's going on, basically. And we'll talk about that. So this is a point of view from performance, essentially why performance is important. And in order to understand performance concerns in distributed systems, you need to have observability. That's kind of the point. Otherwise, you won't know where the performance issues are coming from. So this is really just underscoring the why. The chart on the right shows you a time. It's the time axis in seconds, and it's showing you the number of sessions. So the golden towers are the number of sessions, and you can see that if it takes a very, very short time to run a session with, let's say, a website, whatever the session is with, then basically you don't have that many sessions because they're all completing quickly. As the number of seconds to complete a transaction increases, you can see that it kind of peaks out over time. And you get to the point where you're going to have a lot of active sessions because it takes a while to support those sessions. And then as you have further and further increases in the time it takes to process something, the number of sessions drops off. Now, that's not because you're getting more efficient. In this case, it's because people are getting frustrated and not joining. In fact, they may even decide not to use the service anymore. So if you get too long of a time, like at the tail end here, people just aren't going to bother using the service. So the number of sessions really drops off. So that's what the golden bars indicate. The line is conversion rate. So as you probably know, what we're talking about when we say conversion rate is having customers that are preferring to use your service over alternative services. So it's kind of a good thing to have high conversion rate. And the curve sort of follows a similar pattern. If you have very, very low time to process, the conversion rates are actually low. And I think that's just because there's really not enough data to even validate. But if you look at the longer period of time, the very long time for processing, there aren't a lot of customers in the first place because people aren't really wanting to use the service. But as you start making the system perform better, in other words, respond quicker and quicker in fewer seconds, you get a very rapid increase in the conversion rate. People are preferring to use the service. And so this is kind of an average that was tracked by the DevOps Institute. There's a couple of other specific customer use cases that corroborate that idea. So for example, Walmart found that for every second improvement in the page load time in a web page, let's say their e-commerce web page, they get 2% more customers. So there's a correlation between speed of response on their website and customers. And it could be number of customers. It could also be, a number of purchases as well. So Mobify is another use case, customer use case that found that every 100 milliseconds improvement in their homepage load time resulted in a 1.1% increase in conversion. I always find it funny when they give these 3 digits in this kind of thing. It doesn't, but I don't think that's that significant. But it's definitely showed that there overall is a significant increase, a 1% zone in business basically when you improve the load time. So the statement here, slow is the new down, is kind of indicating that if things get too slow, customers literally don't use the service, it might as well be down. I mean, that's an exaggeration, but that's the idea. The point is that performance definitely does impact business. This is one form of performance, which is demonstrating with actual data that it's true. So we definitely care about monitoring performance and getting data to be able to do that. Now, understanding performance in complex architectures is not that easy. Complex architectures have a lot of data being generated from the different components of the systems, whether it's a large, complex, even monolith, let alone a system that has many microservices all networked together. But generally, you're going to get a lot of data. And if you may have gaps in what you can observe. If you have a lot of points to observe, maybe you haven't got access to some of those things to watch, and that can give you a gap in what you can see or have visibility gaps. You also have a lot of increase in activity. Maybe you've got, because of DevOps and other things, you may have more frequent releases, and that gives you, a time concern and maybe even compatibility of release concern with your monitoring tools as things change very quickly. And generally speaking, there's going to be a lot of different, cases where, depending on what the data is, different people need to look at it across a complex system. So connecting the right data to the right stakeholder is also a concern in complex architectures. It's from an observability point of view, really what observability is talking about is providing not only high-level overviews of the system's health, but very granular insights into the impact of failure modes in the system. An observable system furnishes ample context about its inner workings and helps to unlock the ability to uncover deeper systemic issues. Monitoring, on the other hand, and often you hear people talk about monitoring versus observability, which isn't exactly a correct way to say things, but nevertheless, monitoring, on the other hand, is best suited to report the overall health of the system and derive alerts. So we'll explain why that is. But what we'll also find out is that monitoring and observability really work hand in hand. But observability helps you get access to data that you may need to monitor, or you may need to use monitors to see. There's a lot of relationships. So this is just looking at different architectures, demonstrating how the shift from one type of architecture to another creates additional challenges for monitoring and observability. this could be viewed to some extent as almost a maturity graph from left to right, but not necessarily. It doesn't mean, every architecture should necessarily be cloud native, but the so-called more modern architectures tend to be. But the left side, you got retain and optimize. In this case, you've got, they're showing a data center hosting machines. It could be virtual machines, but they're basically hosted in a data center. You've got a lot of different applications. Each of them may have their own VM, or maybe they'll be distributed and deployed over multiple VMs. Usually in this circumstance, you've got, relatively slower deployment cycles because you have a lot of things to test and get right and integrate in order to make a system. And the dev folks and the ops folks tend to be separated a little more in their day-to-day work, mainly because releases tend to live a long time. So there's not as much of a need for dev and ops to communicate, I suppose. Now, dev's building a lot of changes while ops is working with the last batch of changes in the last release. So that's another way to look at this. So, there's still a lot to monitor though. But to some extent, you're going to be monitoring kind of the outside of the system and not so much the inside of the system, because it's being delivered as a big unit. Lift and shift. This is where you're taking, the components and making them available to work in the cloud. And in this case, as you do that, you're going to move some of your operations activities to the cloud and take advantage of cloud service providers' capabilities. There's a lot of ways to do that. Certainly one of the most popular approaches to start with, at least, is to simply shift your infrastructure so all the VMs can run, in the cloud, not just in your data center. You may have a hybrid situation where some of the VMs are working in the data center, some in a private cloud or a public cloud, but essentially sharing resources across data center and cloud. In this case, you tend to have a lot more interactions going on between dev and ops, because a lot of the solutions being provided by the cloud, and ops needs to get involved, and that dev is not really developing the cloud services. You're buying them essentially, and ops is operating them. And from this point of view, monitoring and observability still are important. It's getting to be a little more complex. There's more things to keep track of, and it's a more dynamic situation. So observability starts to become more important again. The third level here is called refactoring, where you essentially break up the monolith of the big applications, make them more, cloud ready. At least they can take advantage of the ephemeral, dynamic aspect of the cloud. So let's say you have some part of your system that needs to spike in its capability because of variable traffic loads and things like that. Rather than having to stand up an entire new app, you only, you can maybe just bring up the portions that need more capability and traffic capability. So in this case, you definitely have a lot of collaboration between dev and ops as you essentially break up or shard your system into microservices or other service-oriented structures that can run in the cloud. You have to keep track of the interdependencies pretty well. So there's a lot of need for dev and ops to collaborate so that you can keep each other informed of what's going on and be able to operate the service. The full right side is cloud native, where you've fully re-architected your architecture. In this case, dev and ops are very closely coupled because a lot of stuff is happening almost in real time. Releases are happening a lot quicker, and changes can happen very fast. In this case, cloud is now your first choice for architecture. You can still have a private cloud, but you're going to use more cloud services that are ephemeral and stand up infrastructure, or even SaaS, or functions as a service, or platforms as a service. Different cloud services could be used, and it gets a lot more complex to manage, but you get all that flexibility with the cloud. So that's the advantage. Generally speaking, the advantages outweigh the complexity, as long as you're able to manage that complexity. And this is what this is all about. How do you manage the complexity in order to take advantage of the flexibility?